So we are actually finishing up on functions and their derivatives and what we can do with them with this lesson. Next unit, we change gears completely. We look at non-functions, so circles, other equations where, like, for an x, you might have multiple y's. We'll look at tangent slopes of those. We'll do some calculus word problems next unit. That'll be fun. And then in Unit 6, we start going backwards. You'll see what I mean by that. Antiderivatives, yes. We'll start talking about antiderivatives and what we can do with those. So by going backwards, literally, we're going backwards. Okay, to finish off, derivatives and what we can do with them, function analysis, we are going to use tangent lines to approximate function values that are not easily found by hand. So our goal of today, given a function, is to approximate something like f of 1.1. If I asked you, without the calculator, to take 1.1 and cube it and add 3 times 1.1 squared, you'd say, no thank you, I have better things to do. And that is correct. But you at least would be able to say, but you know what, Mr. Messner, I can give you a value that it's like kinda gonna be close to. Discuss with your neighbors. What's the value that it's going to kinda be close to? Yeah, it's going to be close to 4, right? Because you know that this function has the point 1, 4 on it. Well, if I look just to the right of it, I can guess that it's going to be kind of close to 4. Great. But we can do better than that using a tangent line and this fact. If I look at a function and I zoom in anywhere on a function, this function has the point 0, 0. Watch what happens if I zoom in at 0, 0. And I keep zooming in. What do you think is going to happen if I keep zooming in? Discuss. Right. What is this piece of this curve will get flatter and flatter and flatter until it's essentially a line. I guess we should do one more time so that we could see a line. Okay, great. So if I zoomed in right here, I just get a line. Well, that means if I have the equation of this line, maybe I can do a good job approximating some function values very, very close to this particular location. That's the idea. This is called a local linearization of a function. If I zoom in enough at any point of a function, we'll just see little teeny tiny straight lines.
Less than 21. What is that?
Local.
Oh. Sorry about that.
Okay. Zoom in enough on a function, and curves become lines. So, how can I use that fact to get a better approximation for 1.1 cubed plus 3 times 1.1 squared than just 4? Discuss. See if you guys can figure that out. Ready? The idea is if we produce the equation of a tangent line. At the location that's close to this value, you know, at 1, which is easy to work with, at 1, 4, easy to work with, knowing that if I zoom in enough at this location, my red line and my function will essentially be the same line. Won't be the exact same, but they'll be pretty much on the exact same spots. Instead of plugging in 1.1 into f of x, I could plug in 1.1 into this tangent line equation. And the y-coordinate I get using that tangent line will be a better approximation than just 4. Okay, so let's do that. Please find the equation of the tangent line to x cubed plus 3x squared when x is 1. We know we need a point. I gave you the point. You need a slope coming from a tangent slope generator. Remember that your tangent slope generator generates slopes. It's not the slope. It's a slope generator. So this is not m, but f prime of 1, which is 9, is m. You get y minus 4 equals 9 times x minus 1. Some people forget that. The tangent slope generator is a generator of slopes. It is not the slope. Okay. That line, if I zoom in at this point, will be right on top of this function. We are going to use this equation to approximate values for f that are close to x equals 1. That's what we say here. Okay, so if you want to read that paragraph or just keep that in the back so if you can refer to it, it's exactly what we were talking about. Let's go ahead and estimate x cubed plus 3x squared at x equals 1.1. Well, I will want to put this in a y equals form. I could have done it just because it's easy to like graph, but it'll make things nice and easy to work with if we just move the 4 over. To approximate 1.1 cubed plus 3 times 1.1 squared, which is equal to f of 1.1, I will just take 1.1 and plug it in there, which will be something I can do by hand. 1.1 minus 1 times 9 plus 4. This mimics f of x around x equals 1. Plug in x's into this. And it's just for this situation. It's just for this function at this point 1. So I get 9 times 1.1 minus 1 plus 4. 9 times 0.1. We should know that 9 times 0.1 is just 0.9. It's 1/10. Just move the decimal place over once. You get 4.9. So not only do I think it's 4, I actually think it's probably closer to 4.9. Well, let's see. My function, let's go zoom standard. Get rid of this tangent line. Let's find the value at 1.1. 4.96. Okay, so my approximation is a lot better saying it's 4.9 than if I just said it was 4. Pretty cool. Now let's go ahead and do x equals 1.01. Why don't you guys find what 1.01 cubed plus 3 times 1.01 squared is approximately. Again, we know it's definitely going to be close to 4. It's going to be closer to 4 than 1.1 was. X equals 1.1. Why do I know it's going to be closer to 4? Right, because 1.01 is closer to 1. I know I have the 0.14. So I know it's going to be closer to 4, but we can even do a better job because this approximation is going to be even better than just saying it's close to 4. We end up with 0.09 plus 4. I think it's approximately 4.09. Watch. If I plug in 1.01, the actual value of 1.01 cubed plus 3 times 1.01 squared is 4.0906. Very, very accurate. Okay, just using a tangent line. So this is the last thing we're doing with functions, is we are using a tangent line. We haven't really done much with tangent lines. We've been asked to write the equation of a tangent line, but here's a use of a tangent line. It does a very, very good job of approximating function values. I want to get away from 1. I want you to change it up here. I want to approximate f of negative 1.1 and negative 1.01. Would I use the fact that f of 1 equals 3? No, Ms. Clean, you're shaking your head. Why not? Right, f of negative 1 would not equal 3, and we don't want to use, actually it would be equal negative 3. We want to use points that are very, very close to the points we're approximating. So we would make sure that we understand, a point that is close to the values we're approximating. So I get negative 1, and then this is negative 1 plus negative 2, which is negative 3. Now, let's approximate f of negative 1.1 and f of negative 1.01. Go ahead. You will need an equation of a tangent line. To approximate these seemingly very, very difficult things to do. Now, it's not the tangent line equation we had for the other function. This is a new function. Okay, so it's a new function. I need a new tangent line. Make sure you are finding that new tangent line equation. F prime is 5x to the 4th plus 2. F prime of negative 1 is positive 5 plus 2, which is 7. Okay? That gives me my y minus my y1 equals my m times x minus my x1. And I'm just going to go ahead and solve that for y. Without distributing, it will be much easier to work with. Okay? To approximate negative 1.1 to the 5th plus 2 times negative 1.1, which is f of negative 1.1, it's going to be approximately 7 times negative 1.1 plus 1 minus 3. All right, you do the math, figure out what we get. I get negative 3.7, and I know that if I got closer to the actual value, so if I did negative 1.01, approximating f of negative 1.01, I'm using an x value of negative 1.01, and I end up with negative 3.07. Okay, and I'll see that it's close. Log values. The log of 1.1. Nobody has any idea what that is, right? Well, I know what the log of 1 is. What's the log of 1? This is important. You guys need to be able to say, oh, okay, 1.1, that's close to 1. I actually know what the log of 1 is. All right, so good. Let's find an equation of a tangent line to the log function at x equals 1. Let's see if this is difficult. Let's see. F prime, what's the tangent slope generator for log x? 1 over x, good. At 1, I get 1. So I get y minus 0 equals 1, x minus 0. That's just a tangent equation of y equals x. So get that thing out of here. Oof. Very disrespectful. Am I right? I think the log of 1.1 is close to being 1.1. I literally just typed in y equals x, so I plugged in 1.1 in for x. I got 1.1. Let's see. This one might be confusing to you, but the next one will be cool. .09, that's not great, but that's what it is. That's a good question. No, I don't care about radians.
Were you in radians?
Yeah. So like, because of the log function, it doesn't work great. But watch. So not a great approximation, but at least we have a general idea. We're in the ballpark, okay? Square roots of values. Square root of 17, square root of 15.5, okay? I don't know what they are, but I know that they're going to be close to 4 because I know the square root of 16 is 4. All right. Let's use a tangent line to have good approximations for the square root of 17 and square root of 15.5. Trust me, they will be better than 1.1 and 0.09, which wasn't that bad. Okay. Discuss with your neighbors. What do you need? You need a tangent line equation to the square root of x function at 16.4. So I need my tangent slope generator to generate a tangent slope at 16. Oops. Okay, get this, which turns into that. Here's where people falter. They say, okay, trying to approximate the square root of 17. They then go ahead and plug in root 17 in for x. And then they look at that and they're like, I don't know what to do here. Like, I don't know what the square root of 17 is. But you're not thinking about it the right way. Discuss with your neighbors why you don't do that. Ready? This will give you a hint. When we wanted to approximate negative 1.1 to the fifth plus 2 times negative 1.1, I didn't plug this in for x, right? What did I plug in? Just the negative 1.1, f of negative 1.1. When I wanted to approximate 1.1 cubed plus 3 times 1.1 squared, I didn't plug in this entire thing, the y-coordinate, in there. I just plugged in the x-coordinate. If I'm trying to approximate the square root of 17, what do I plug in? Just 17, because this is f of 17 when x is 17. Okay, now do a little bit of arithmetic. Tell me what the approximation for the root of 17 is. Plus 4. You need to be able to do some arithmetic with fractions. 4 over 1, multiply the top and bottom by 8, you get 32 eighths. 32 eighths plus 4, 33 eighths. Okay, you guys tell me the approximation for the square root of 15.5. You have to do a little bit of arithmetic here. I would not use 0.5, I would use 1/2 whenever you start doing the calculations. Let's see what we get here. Go ahead. Check your arithmetic with your neighbor. Yep. Okay. Yep. Yep. You got to turn 4 into something over 16. The cross multiply is not what we do at all. We find a common denominator. We're good. Okay. Let's just work with fractions here. That's negative 1/16 plus 4. You need to turn 4 into something over 16. That's 24 times 4. That's 64 sixteenths. 64 sixteenths minus 1/16 is 63 sixteenths. That's arithmetic, not algebra. Okay, so let's see how we did. Now the actual square root of 17 is 4.123. Okay, close to 4, like we knew. But we did better. We said it's not going to be close to 4, it's going to be close to 33 eighths. 4.125. It's really good. Now, is my approximation 63 sixteenths going to be closer to the actual than my approximation for the square root of 17, or further away from the actual? Closer, because 15.5 is closer to 16 than 17 is. Let's see. The actual square root of 15.5, which will be close to 4, we know that, is 3.9370. 63 sixteenths is 3.9375. Okay? Accurate to the 1,000th decimal place. Pretty cool. Okay, now I set it up for you to kind of know what to do for this previous situation. You will see sometimes just this. Approximate the cubed root of 9 using a tangent line. Okay, go. Talk about it with your neighbors. What would you need? What would you use? I know what it's going to be close to. At least I know a starting value. Cubed root of 9, what's it going to be close to? The cubed root of 9. Close to 2. Why do I know it's going to be close to 2? Because the cubed root of 8 is 2. Use that. We need to use that the cubed root of 8 is 2. Don't just take a stab at it. Let's actually get an accurate approximation. So, we need, and this is important because you'll see this, you need a function, the cubed root of x, and you need a point on the function. F of 8 is 2, which is close to the point we're trying to approximate. Okay, go. You'll need to figure out what 8 to the 2/3 is, which I hope we can do by now. So I need my tangent equation at 8, 2, which means I need the tangent slope generator with 8 plugged in. Tangent slope generator is 1/3 x to the negative 2/3. That's going to be 1 over 3 x to the positive 2/3. I plug in 8. I need to know that 8 to the 2/3 is the same as 8 to the 1/3 squared. So that's 2 squared, which is 4. So this is 1/12. Y minus 2 equals 1/12 x minus 8 is my equation of my tangent line to the cubed root of x at the point 8, 2. The cubed root of 9, which will be f of 9, will be approximately, do the arithmetic. We get 25/12. 2 is 24/12. Let's see. How do you plug in the cubed root of 9? 9 to the 1/3, not 3. Make sure you use parentheses if you have the old operating system. 2.08008, 25/12. 2.083. All right, cool. Now, not only can I produce really good approximations, but I will be able to tell whether or not 33/8 as an approximation for square root of 17 is going to be above the actual value or below the actual value. So let's talk about over and under approximations. I'm going to draw the situation, tell you whether or not we have an over approximation, and you will tell me the difference between the functions. Okay, so I have a point in black that I'm going to draw a tangent line to that I'm going to use to approximate my point in red. So if I'm on the tangent line, this blue dot would be my approximation. The red dot would be my actual. We would call this an under approximation. because my approximation is under the actual. It'll be less than the actual. In this situation, if I use the black dot, a tangent line at the black dot, to approximate the red dot's value, my approximation on my tangent line is going to be over the actual. What is the difference between the two functions that you see? Discuss that with your neighbor. I love how we look and notice the difference in the concavity. This is concave up, this is concave down. This means its second derivative is positive, this means its second derivative is negative. Now, before we move on, I have a question for you. Both of these functions are increasing. If f of x was decreasing, does the situation change? Would my over approximation stay over, or will they become under? Discuss. So if this is still concave up, but we are decreasing concave up. This is still concave down, but we're decreasing concave down. Does it change whether or not you're increasing or decreasing? What do we think? We got some changes, we got some stays the same. We think same over there? Changes over there? Well, if you were in the stays the same, you are correct. Look, no matter whether I'm decreasing concave up or increasing concave up, my tangent lines, all of the values on my tangent line are below the curve, under approximations. All the values of my tangent line, if we are concave down, decreasing, above the curve, over approximations. So if we just know concavity, if concavity is consistent between our point that our tangent line is passing through and the point we're trying to approximate, we'll know if it's over or under. So before we just, let's just go back originally to square root of 17, which I brought up. I think it's approximately 33/8. You probably don't remember from the calculator if it was over or under the actual. You will be able to determine if it's over or under the actual. How? By looking at the concavity of the function. How do you examine the concavity of a function? Second derivative. So, my function was the square root of x. Its first derivative was 1/2 x to the negative 1/2. Its second derivative will be negative 1/4 x to the negative 3/2. Now, just like normal, I should be doing a sign analysis of this. But I don't have to go crazy. We are looking at the square root of 17. Okay? So that's like starting at the point at 16. As long as I know what the sign is between 16 and 17, I'm fine. We will find that with the square root of x, the signs will be consistent anywhere x is positive. Now this is interesting because I can't plug in a negative value into the square root anyways. So there is a starting point, but we should, if we want to, at least think about the area in which we're examining the second derivative. I'm really only concerned about between 16 and 17. But really it ends up being the same in this case after 0. You can either plug in 16, plug in 17, or think about if I plug in a positive value into f double prime. I'll have a negative divided by a positive. These are all negative. To the right of 0, f double prime is negative, which means the square root of x, which you know is concave down. Now, I don't want you to memorize what we produced earlier. I want you to be able to draw a picture. If you have a concave down function and you have a tangent line, would your approximation on your tangent line be over or under the actual value on the function? Figure that out. Will 33/8 be an over or under approximation, knowing that the graph of the square root of x is concave down? Go, discuss. This is what you do. Concave down, tangent line, over the actual. 33/8 is going to be close, but I know it's going to be over the actual. 63/16, was that our other approximation? Will be a little bit over the actual. Go back to the calculator. 63/16, 3.9375, 3.9370 over the actual. Not only do we have a good approximation, you could say, hey, I can give you an approximation, I can tell you if it's going to be over or under. 4.125, 4.123, over the actual. Okay? So like, sometimes you won't even be given a function. Sometimes you'll just be given all the information you need. This is really, really great. You can immediately write an equation of a tangent. You can approximate a function value. I get negative 0.2 plus 3. That's going to be 2.8. Not only can you find the approximation, but now, with your neighbors before you leave, tell me, is this approximation over or under the actual value if g double prime is positive? Draw a picture. Most of you are all over this. If g double prime is positive, the graph is concave up, a tangent line would produce under approximations. I will continue these notes and finish them. F of 2 is 12. I'm approximating f of 2.1. Let's change this to like 2.2. Sometimes like the 0.1s, they're easy to do. We need to be prepared to do something a little bit different, maybe using fractions. I got a point. I need a tangent slope for a tangent line equation. I got a slope of 12 of y minus 12 equals 12 times x minus 2. F of 2.2 will approximately be 12 times 2.2 minus 2 plus 12. 12 times 0.2. Different ways to handle 0.2, 0.25, stuff like that. You can either do the arithmetic, and 12 times 2 is 24, move the decimal place over, you get 2.4. Or you could change this into a fraction. 0.2 is the same as 1 over 5. It's 2 over 10, which is 1 over 5. So you can handle this two different ways. Either 12/5 plus 12, 65 plus 12, 72/5, or 2.4 plus 12 is 14.4. Okay, 72/5 is the same as 14.4. Okay. Great. We already know how to do that. That's great. Over or under? Examine the concavity. You can see you're going to change concavity at 0. Maybe you wanted to put that down. You actually don't care. You would focus your attention on your second derivative between 2 and 2.2. So as long as the signs are consistent between 2 and 2.2, that's all you care about. You can see they're positive to the right of 0. That means f is concave up. Draw a picture of something concave up. Draw a tangent line. Concave up, tangent line. My tangent line approximations are under. Yes. Yes, I don't look at the approximation at all. What do you mean? Like, I look at my second derivative, which is 6x. And like we always did to examine signs of things, we could set this equal to 0. And I could do a full-on sign analysis of f double prime. F double prime. 0 to the right of 0, it's positive. To the left of 0, it's negative. Gotcha. Okay. You could do the full-on sign analysis, or you're really just concerned about a specific location, a specific interval. Okay. This is a good question. Just making sure you understand and can draw a picture. This is all about drawing a picture. We got a second derivative that's positive and a first derivative that's positive. Draw f that has those characteristics. Second derivative positive, first derivative positive. We should be drawing that. Right? You all got that? Increasing concave up. Let me be a little bit more exaggerated. There we go. We have a secant line drawn from f of 0 to f of 2 and a tangent line drawn at 1. Well, let's just like split this into 0, 1, and 2. So I got a point at 0 and a point at 2. Draw a secant line. There is S of x. Draw a tangent line at x equals 1. All right, so at x equals 1, I'm going to draw a tangent line. Maybe it's like a mean value theorem situation. Maybe it's not. The slopes don't have to be equal. That's good. All right. So this is t of x. That's s of x. And then, we have our f of x. List in order from least to greatest. F of 1.1, t of 1.1, and s of 1.1. Go. Least to greatest. So now we're thinking about what are my points here at 1.1. we'll just draw some points. You got t of 1.1, f of 1.1, s of 1.1. I guess I should do this one in blue. Because the function's concave up, I know my tangent line approximation is under. I know my secant, just from the graph of something increasing concave up, is going to be above. So least is t, then f, then s. And that's it. Here we go, John. Okay. One other thing we could do is approximate the location of a 0. A 0 is an x-intercept. It's when y is 0. What we are going to be doing is, if we know we have a point that's close to 0, let's just change that to 1/2. Okay, so I know I have a point at x equals 3, the y coordinate's 1/2. This is an easy point I can work with. And I know that the tangent slope of 3 is 2. Well, here's my equation of my tangent line. What we will be doing in this situation is finding the x-coordinate when my y is 0. So we can kind of approximate when does my curve pass through the x-axis. We will go ahead and plug in 0 for y, and we will find x. Okay, so I got negative 1/2 equals 2x minus 6. Does help to distribute there. I add 6, that's 12/2 minus 1/2, I get 11/2. Okay, it's going to be close to at x equals 3. I can see it's a little bit to the right of it, left of it. Same thing here. Now, I don't give you a point with a y value close to 0, but you can find and pick a point that works out well. I know f of 0 is 1/2. 1/2 is close to 0. F prime of x, 3x squared plus 1. F prime of 0 is 1. I have an equation of a tangent line. When y is 0, find x. Negative 1/2. Okay. Watch. Y equals x cubed plus x plus 1/2. I'll also graph y equals 0. Where is this 0? If I find the intersections between the two, negative 0.42. I got negative 0.5. Pretty close. Okay, the closer I had a y coordinate close to 0, the better my approximation is going to be. And that is it. That is it for Unit 4.